So let's start this great day about the tractometry and peering into the white matter by speaking about the organization of the white matter association pathways. In fact, I'm not going to teach you the exact organization of the association fibers of the white matter of the human brain. Because to be quite honest, we don't know it all that well. Of course, most of you already heard about some famous association bundle like the arcuate fasciculus connecting the frontal cortex with the temporal one, or the inferior fronto-occipital fasciculus, the IFOF connecting the frontal cortex with the posterior lobes through a ventral pathway. And we may still describe most of them for 30 minutes, speaking about their cortical origins or their pathways and their putative functions, debating about the names, the nomenclature of them. But instead, what I would like to do today is to give you the keys so that that with everything you're going to hear today along the different talks, you will be able to imagine what the different tractography approaches are trying to reconstruct from this anatomical ground truth that needs to be improved also. And not also that everything that will be presented here is at the macroscopic level, I would say at the fiber-wise level, in the sense that the filament-like fibers visible on the dissection scenes or the streamlines in tractography encompasses a large number of axons. So let's start with some historical points about the organization of this white matter. It is generally accepted that Theodor Meynert established with a greater clarity the three principal types of white matter systems that has been first suggested by the end of the 18th century by Vic Dazier. Vic Dazier discriminated between the callosal and association systems. And a little bit later, Gall and Spurzheim discriminate between the projection system and an association system, including the callosal fibers inside. So this is Meynert who really clarified everything and beautifully illustrated that in this book by saying that the fibers of each hemispheres anatomically unite distinct convolutions separated by sulci, and these have the name of association fibers. And he said that they are the expression of the unity of the brain to which they belong, just as the projection fibers are the expression of the diversity of the organs and body surfaces to which they distribute via nerve pathways. Then he's introducing the notion of corpus callosum and anterior commissure to discriminate that the corpus callosum differs from association fibers in that it connects identical sites in both hemispheres rather than different sites in the same hemispheres. And something important also is that these callosal fibers are traveling toward the convolutions when they are intermingled with the projection and association fiber system. I would say a word on that in a few minutes. So for 150 years now, we are considering three types of white matter since Meynert, which are the association fibers with both termination in the cortex of the same hemisphere, the commissural fibers linking the two hemispheres with one termination in each hemisphere, and the projection fibers with one termination in the cortex and the other one in the gray nuclei of the striatum, thalamus, brainstem, up to the spinal cord. And as mentioned by the Meynert works, the commissural fibers intermingles with the projection of association and fiber system. And this is something perfectly well described more recently in the macaque monkey brain, thanks to the tremendous work of Jeremy Schmaman and Deepak Pandya, and which has been summarized here with the famous representation of the organization of the white matter pathways. And so these authors said that in their course, the association fibers either remain confined to the white matter of the gyrus, or they travel deeper in the white matter of the hemisphere, and there are some short association fibers or U-shaped fibers which are linking adjacent gyri, and neighborhood association fibers link nearby regions, usually within the same load. They also discriminate the course of the strial fibers, the projection strial fibers, which are intermingled with the association fibers early in their course, and they are identifiable as distinct fibers in the white matter. And they also introduced the notion of cord fibers, which segregate into the commisural fibers and some projection subcortical bundles, which further subdivide in fibers destined to for the thalamus or the brainstem and spinal cord of the pontine bundle. Anyway, this is a clear explanation of the organization of the different types of white matter. And then now we're going to more focus on the association one. And so to finish with these historical points, but I think it's always important to remember how our knowledge were acquired and what it's based on. The reference is also often made on the work of the Desjardins, Jules and Auguste Desjardins, who at the turn of the 20th century published two still influential books about the human brain neuroanatomy. And speaking about the association fibers specifically, they clearly describe that the shortest of these fibers are also the most superficial one, immediately lining the bottom of the circuit. As they are removed, the valleys become wider and the fibers become longer. Sometimes these fibers pass over the base of the nearest convolution to connect two distant convolutions, or even two very distant territories. And thus, it's forming the long association fibers in this later case. They also said that the intermediate fibers are found between the U-shaped fibers and that connect two neighboring convolutions, and the longest one, which give us a very important rule that they said as a general rule, which is the short fibers, association fibers, are always the most superficial, closest to the gray matter, while the long fibers are the deepest. So it can be represented coarsely like like this, but with some U-shaped fibers around every sulcus and then neighborhood connectivity and so on. But it does not mean that each part of this cortex is connected to the rest of the hemisphere with all these different type of short and long connectivity, at least at the microscopic level. The things are organized in different bundles, and we're going to speak about that now. But again, no one can fully describe this exact organization of all white matter association fibers at each point, at each hemisphere, sorry. So this is why we are usually saying that we still need the ground truth in terms of white matter anatomy to be used for better, reliable tractograms. And this will be, probably there will be many occasions today to address this issue, I guess. So to have a very good idea of such organization of the association fibers, I will recommend to read this article published 3 years ago in Cerebral Cortex by Shinohara and colleagues that used the Klingler dissection method to describe the association fibers from the most superficial ones, the U-shaped fibers, to the longest and deepest one. But before, let me introduce you for the people that are maybe not familiar with the technique, what is the dissection method a la Klingler. So in the mid-1930s, Joseph Klingler developed a method that facilitates this separation of the white matter fibers during dissection. Once you fixated the post-mortem brain with formalin, the technique of Klingler is to freeze at least 2 weeks at -50 degrees the brain. So the majority of the aqueous formalin solution does not really penetrate into the myelinated fibers, but we know that they remains they remain between the fibers. Then with the freezing, the ice is formed between the fibers. And since the volume of water increased by about 10% when it solidifies into ice, the fibers are thus separated from each other. And this losing up of the brain substance facilitates the dissection, and it allows better understanding of the white matter organization since this seminal work of Klinger. Today, the Klinger approach is the reference dissection technique, which has been improved almost 10 years ago by a cortex-sparing Klinger dissection approach. In that case, the dissectionist first starts to remove the most superficial layers of the fibers, and then step by step follow a specific bundle, but the goal is to preserve the cortical origins of the bundles as long as possible during the various stages of dissection, in order to better understand not only the bundle pathway, but also the cortical termination. And we can see on that pictures that step by step, the cortex is kept in order to better understand from where these fibers of the arcuate fasciculus, for example, are coming from the temporal cortex. So going back to the study of Shinohara et al., they applied the classical Klinger dissection approach, not the cortex-sparing one in that case, because they want to really study first the first superficial layers, the U-shaped fibers. So to do so, they have decorticated the gray matter along the major convolutions in the temporal, occipital, parietal, and frontal cortex. And they revealed white matter ridges that follows the gyral convolutions and their junction. We can see them here, and they are both intragyral and intergyral ridges like that, that are principally made of upright U fibers. And the white matter, which floors, or the white matter floors of the sulci are paved with a different curve of these U-shaped fibers. So this is a description which fits perfectly with the pioneering ones from Desjardins, for example, as I mentioned earlier. And these authors also mentioned that there are some, as I already said, intragyral and intergyral U-shaped connectivity, which could be followed all over the brain. And here we are just a focus of what is going on in the temporal cortex. And interestingly, by continuing the dissection deeper, the longer fibers appear between more distant convolutions up to the longest ones. We can see step by step that after the intragyral and intergyral U-shaped fibers, when you're going deeper, you get some longer fibers with longer pathways, and again, deeper and deeper appears the longest one. So this is a very convincing demonstration of what Desjardins said. The Desjardins said and published or described almost 120 years ago. So considering now the longest association pathways that are usually the most studied one, in fact, one may ask finally how to characterize them in order to extract correctly these bundles or subtract or tracks from a whole brain tractogram, for example. So defining an association bundle means, for me, characterizing a set of groups of group fibers or streamlines that follow the same pathway to correct a region A with a region B, which is quite obvious. Thus, I would say that what characterizes an association bundle is its bundle stem. I mean, the way all the fibers belonging to a specific bundle are passing through. And what I'm going to call the gyral stem shell regions, which is determining the cortical termination of a bundle. And I'm going to explain later what is this gyral stem shell notion. Starting first with the bundle stem, let's take the example of the dissection of the inferior frontal occipital fasciculus to understand better what is this notion of bundle stem. Once in the dissection of the IFOF, the dissectionist is starting by removing the insular gray matter to reveal that part of the brain, which you can see that you've got some fibers going between the frontal cortex and the rest of the posterior part of the brain. And then by locating the arcuate fibers of the uncinate fasciculus from the temporal cortex, the temporal pole of the temporal cortex, and the frontal cortex, it's then possible to discriminate a series of fibers and a density and higher density of these fibers. And the dissectionist is just not taking a paper and make a paper tag of this stem, then is able to follow every in the two directions, the description of the IFOF in the frontal cortex or in the temporal and parietal occipital cortex in the posterior part. So this is how we can discriminate and we can define what is a stem for a bundle. And it's interesting that you can apply exactly the same approach with the tractography data. You can remove the fibers, the streamlines, which are hiding the region of the stem, and then step by step, by filtering out some streamlines, you can locate the stem of this IFOF, then use the regions of interest, not a paper tag, but the regions of interest here, to then consider that everything which is passing through these regions of interest is going to correspond to the stem of the IFOF. And then you're going to extract all the fibers, streamlines of the IFOF without any a priori of the termination of the bundle. Which means that with this kind of approach, it's possible to really replicate what you observed in dissection by tractography, by applying exactly the same type of extraction of the bundle, using only the location of the stem, I mean, where all the different parts of the bundle are converging in the same place, which is very similar to what was described for the first time at the turn of the 20th century by Curran to define for the first time the IFOF. This is also something that we can observe in a macaque brain, in a monkey brain, which is a favorite monkey brain here, where you can apply exactly the same approach to extract the stem of the IFOF, both in dissection and in tractography in the same animal. So it's going to be a study published now 4 years ago, where we revealed the existence of this IFOF in the macaque brain by doing this dissection and tractography in the same animals. So the last thing I would like to set up today about the organization of the association fibers, at least in the context of these deep, long-range association bundles, is the notion of gyral stem shell. As I mentioned earlier, we are considering that the different types of fibers entering or leaving a gyrus are represented that way. I mean, with the famous drawing coming from Schmamann and Pandia. And the gyral stem shell approach means that whatever a tractography algorithm in generating a streamline, the anatomically plausible streamlines have to respect these rules. I mean, the fact that the white matter fibers enter or exit a gyrus, regardless of their length, which is for the shortest one or for the longest one, through this gyral stem, this door of the gyrus. And under no circumstances do they extend beyond the utmost layer of the cortex, which I call the shell, and thus they never cross a sulcus. This may seem totally obvious to you, but in fact, a considerable number of streamlines that are then considered as false positive and has to be filtered out are produced in the whole brain tractogram, whatever the algorithm you are using, just by not respecting these obvious facts that Y build streamlines that are crossing sometimes the sulci of the around the brain, and not at the first time just keep everything which is entering a gyrus and never cross the surface. And here is an example of the application of this gyral stem shell filtering, which was in order to extract the different tracks connecting the angular gyrus and the validation of them with the cortex-sparing Klinger microdissection techniques. And here, for the long-range angular connectivity, you can see that it's possible to have a clear representation of the bundle connecting the angular gyrus with the middle frontal gyrus, both in dissection and in tractography. Same for the inferior frontal gyrus with the angular gyrus, or the precentral cortex, for example, here. And it was also interesting to observe this shortest connectivity with the angular gyrus with some neighbor gyrus, like the supramarginal gyrus, post-central gyrus, or the superior parietal gyrus. And you can see that we have a very good representation in tractography, which is very similar to what is expected and observed in dissection. But speaking about validation of this tractography data with dissection, I would like to end this presentation by quickly introducing a tool that may interest you. Its name is Bradifo. Bradifo is for brain dissection photogrammetry, and it will be soon available. And for the first time, it's going to offer to everyone an access to dissection data, and especially dissection data that can be reconstructed in 3D virtually and can be used to merge tractography on them and see what's going on in terms of validation when you observe, as again, I mentioned earlier about the angular gyrus and the middle frontal gyrus. You get this type of tractography in vivo. And with Bradifo, you will be able to merge this data on an ex vivo or other ex vivo brain and see if you are respecting exactly the anatomy of this tract connecting the angular gyrus with the middle frontal gyrus, for example. So, in conclusion, I would suggest two main messages when thinking about the organization of the white matter association pathways, which could be discussed all the day with some different example of tractography and extraction of bundles that we will see and we can discuss all that day. And so the two things are the shortest fibers are always the most superficial, closest to the cortex, while the long fibers are the deepest. And also an association bundles is characterized by its bundle stem and cortical termination. And this latter should respect a gyral stem shell organization to avoid spurious streamlines, which are coming from the bad way when entering a gyrus, for example. So thank you very much for your attention. I mentioned here all the colleagues and friends which are collaborating with me about this kind of topics of studying the association of white matter pathways. And now I'm open for discussion and questions.